someone was, but it's funny. Okay, so last time we figured out how to, why are we using x-rays for what we are doing? I just lost my chalk. Yeah, I'll find it later. There it is. Why we're using x-rays to look at crystal structures. Today, what we're going to do, we're going to take Bragg's law a little bit further and figure out how do we actually determine structural information from this. So we saw that we can get unit cell lengths, but how do we get more information than that? So question, how do we get structural information from this? Okay. So what we need to do, we need an expression to derive the distances between planes in a crystal based upon Miller indices. So that way, if we look along different angles, we can get more information that way. So we need to derive an expression. The distance between crystal planes with the Miller indices H, K, and L. Super squeaky on this floor today, sorry. The reason for that is we're going to hold a rolled tissue box as an example. If we want to look along different directions of this crystal, if we add up all those different directions and distances as we look at this thing, we should be able to get all the information we need for a crystal. We're going to start with an easier expression using the Bragg's law. And then we're going to move on to something more complex called atomic form factor, atomic scattering factors, and structure factors. Okay, so to do this, we're going to derive an expression for planes parallel to the z-axis. And then we're going to generalize our results to any arbitrary plane. To do this, we're going to look at an orthorhombic unit cell. Yeah.
So, for the exams, like, is it going to be similar to any problems? Like, any problems on like?
I will let you know after today, once I start working on it. Okay, we got an orthorhombic crystal that is three-dimensional, and it's 1 to infinity plane. Okay. We're going to be looking down the crystal. Looking down the crystal, atomic positions are going to be on top of one another. So really, it's going to look two-dimensional for what we're considering. I need one more. Crap. I'm going to do it over here. How many of these do I need? That should be good enough. Okay. Joe, you said yellow and blue are good, correct? We'll need those. Can I use orange to mark the axis in the corner? Okay. That's the y direction. This is the x direction. And where is z? Yep. Pointing towards our eyes. We're looking down it. There's z. Okay. Now, what we want to find the distance between the planes. We're going to call this distance delta. Bless you. Actually, I should have marked this with a bracket for direction. I'm sorry. Okay, if we're doing this direction, 1, 2, infinity, we're going to have a plane that we're looking down, correct? So we're talking about this axis along here. I got to skip these right so I do it right. So bear with me for a second. That's one of the planes we're talking about. That's one of the planes. This one's going that way. So we'll call this plane 1, plane 2, plane 3. Does everybody see that? Okay. We're going to do some trig yet again. We want to get this delta, that distance, correct? So let's draw some right triangles. That distance along there. We're going to call this guy alpha. It's a right triangle that's in there. But we can also bisect this dude and draw another triangle. And we're just going to label this guy, this side S1, this side S2, and the hypotenuse S3. What do we want out of this triangle? We want to find S2. Okay. We'll just use orange. Want to find delta, which is the same as S2, right? We're going to use a triangle. Here's our triangle that I'm going to pull out from here so it looks a little less complicated. S1, S2, There's an angle alpha. And then this dashed line, that's D. So shoot. How could we, so we know that S2 is equal to delta, that's true. Could we come up with another expression for this guy? What would it be? Yes, we could do that. I don't want to touch that one yet. We will get there, though. It will happen. By the properties that we're doing here, you might have to remember from trig. That's true. We will get there, too. How is it related to D? No. Just that. So this, because it's bisecting these guys in the pattern that it's bisecting, it means two of these will fit in here, right? So if I measure, how many times did this thing get cut by planes? Bless you. Woo, bless me. Yes. It got cut twice. Let's just do a quick question. We're not going to use this, but let's see. What about the 2, 3 plane that gets cut, that cuts D 6 times? How would those two relate to one another? Yeah, D over 6. Because that distance along here got cut right in half. Do people see it? For the 6, we'd have 6 lines going through there. Do you at least trust me on that one, or? Okay. We want that triangle to come back. I don't think I need this guy again. Therefore, looking at what we have, a general expression. The Miller planes. H, K, and L is what? So what were the directions here again? Was it 1, 2, infinity? So we're going to leave infinities out. They're never fun to work with.
Wait a minute.
Yeah? So what's going to go down here?
A, E.
Not A and B. Not X and Y.
HL.
Not H, L.
There's HK.
HK.
I was close.
3, 2 times 3?
I noticed that.
6.
That's where I got that.
1 times 2, 2. That's where that's coming from. Okay. Yes. Are you stuck here with the cutting? So back at that picture that I just erased, we're looking at how many times we cut, and we know the lattice planes are equidistant from one another. So check back at your picture where we drew those lines. How many times am I cutting D? 2 times. Okay, so we know that that relationship has to be true.
So it's not a distance?
It is a distance still, but it's how many times we're slashing that distance. So as we look through different planes, we're going to cut it different amounts of times. Okay, we'll start with that and we'll go to something a little more mathematical because it's going to help out. Okay? But what do we really want? We want to get those distances. We want to get lattice planes. I have yellow chalk on my nose. There we go. Well, we want the different lattice lengths. Okay, now let's use the more trig expressions with angles in there. Sine of theta, what's sine of theta going to be equal to? We got a couple different options. Yeah, okay, so there's a couple we want. D over S1, yep. Yep. Those are the two I want. Okay? I'm going to erase this part and keep our triangle around because we're going to need our triangle. We might need that other bit. Okay, so what we can do we really need that angle in between? No, what we can do is say that this portion and that portion are equal to one another. So get D, S1, S2, S3. But again, what are we looking for? Yeah, we're looking for a distance, so manipulate this. What's that equal to? Yep. Okay. Now, D is a little bit different than delta. I just erased our expression for delta. Plugging in for delta. Delta was equal to D over what for a general expression? Yep, HK. Okay, so now let's plug in what we just determined for D here. So what's this going to be equal to? So S1, S2, HK, S3, like that, right? Okay. So now, from the definition of what type of cell are we using? Yep. S1 has to be equal to K times B. What are these things? In which direction? Yep. Okay. And S2, if that one were, if S1, because we're talking about reciprocal space here, S2 has to be equal to what? Given S1 was KB, what do you think S2 will be? H times A. Yep. And what's A again? Yep. Okay. Katie, this is where we're going to use the Pythagorean theorem. Which I totally had to Google how to spell Pythagorean because I didn't know it off the top of my head. Yeah. Okay. What would S3 be equal to using the Pythagorean theorem? I want S1 and S2 for now. Okay. We have another expression for that, though. S1 and S2. What's S1 equal to? Yep. A times B squared. And what's S1 equal to? Yep. No, you're good. It feels backwards because we're using something called reciprocal space, which I don't want to tell you about yet. Mm-hmm.
Why is it so if we're in reciprocal space, why is it actually instead of like
I don't want to talk about that right now. But we can't talk about it right now.
we're just not there yet.
So is it not true that S2 is delta?
S2 should equal delta. It could equal delta. It doesn't. For now, we're going to say yes. It should work. You might be there's a reason we're going about it this way, Katie, because you're like, why the hell? Just solve for S2. Why are we? Because part of the problem is we don't know reflections all the time. Like this time, we're assuming, yeah, we know this, but when you get an output that looks like that, how do we actually know that that is that one? So for the theoretical crystal where we know everything, yeah, we can solve that thing. But when we don't know that crystal, then we got to use this other expression we're deriving.
Is that why when you like solve or know a crystal, it's like a function?
We'll talk about that in a bit too. Let's plug into this guy, that delta. Okay. So delta is equal to S1, S2, all of that jazz, right? Okay, what we can do now is take that S3, plug this stuff in. Oops, sorry, it's K. I forgot to plug one more thing in. I have this luxury, you guys don't, I'm sorry. What are S1 and S2 equal to? Okay, we can simplify this expression. What things are going to go away? Yep, and we're left over with this guy. I'm just going to reorganize some things. Okay, Katie, you're going to hate me more in a minute. Sorry. We're going to do some stuff that seems nonsensical. We're going to square both sides. Okay. We square both sides, what happens to the top? Yep. A squared. And to the bottom, what goes away? Yep. Okay. Now we're going to take the reciprocal. A squared plus k squared b squared all over b squared a squared. Okay. Simplify this. We're going to get two fractions. I want it even simpler.
Oh, do you want to simplify, like cross things out as you do that?
Yeah.
Okay, then it's going to be.
Uh-huh.
Yeah.
Awesome. Okay. So now, what do we get out of this thing? We look at this delta. We only have to consider our planes, and then we know our lattice vectors. Okay. We can generalize this, though. To any crystal with primitive translations So what would this not work for? What type of crystal? Yep, and triclinic. Triclinic sucks. Triclinic's never good. Okay, L H squared plus K squared Okay, so we're going to use this. We possibly have. It may have been hidden in other things. Okay. Now, we're going to pretend that we're going to use powder diffraction. We really haven't talked about powder diffraction a ton. And we're going to pretend we have a cubic unit cell. A cubic cell, what does that tell you? What about the lattice vector lengths? Okay. Then delta, if we look at our delta expression. How's that going to change for a general equation? Yep, and we can pick any lattice vector we want. I like A. So then if we manipulate this through and we want to get delta, what's delta equal to? Mm-hmm. Okay. Bless you. Might be related. We're going to use the Bragg equation. The Bragg equation only cares about what types of intensities or what type of interference? Maximum constructive. So, given we need maximum intensities, the Bragg equation so if I represent the Bragg equation in this way, what's the other side equal to? Yep. Okay. Since we're trying to determine distances between planes, D is going to change to our delta. And we care about maximum intensity, so what do you think we're going to do with that N value? Okay, what we're going to do, let's get sine by itself. What's sine theta equal to? Okay, we have an expression for delta. If we plug in delta, what happens to this equation, or what does it become? Yep. Oh, just A, I'm sorry. Okay, now let's look at this. Experimentally, what do we control? Yep, we control this part. This is the angle at which we're shooting energy at our crystal. What other things do we control experimentally? Lambda. Yep. Everything else we don't control. But what do we know about these things? Don't have to be equal, because it can be any, it will change based upon the angle, right? Those have to be what? They have to be integers. So there's only so many possibilities. We're squaring this, right? So is there a difference between these planes?
No.
No. So we have a set of numbers that we can just plunk in here. And what can we find? We can find the lattice vector from that. So, Katie, you were like, why the hell aren't we just using trig using that angle? Because we didn't know that angle. Like, we don't know it in experiment. This one we do know because we can hit it. We don't really know the planes, but we can guess them. And from that guess, we can figure out a reasonable unit cell length. Okay. I have an example. So part of it isn't from just a guess. Part of it is from what you get as an output as from a powder diffraction. So I'm going to pass out some powder diffraction patterns that you guys want to hold on to for future examples. But if you look, this is the output that you get. You get little spikes. And I've labeled some information. I've labeled the planes for you because we're going to need those planes. But if you use this equation and you use those reflections in the correct lattice parameter, guess what? It works out to what is measured. So you use the experiment that you have there, and you can figure out your lattice vectors from that. Does that make sense? Are there any questions right now? I know that was a lot of hand-wavy trigonometry. We're going to go over an example next time that will relate to this. And then we're going to go into something that is less hand-wavy in terms of this explanation, that is more physical. But I wanted to hit it this way first because this is how it was done historically. We figured out the next bit a little bit later. Okay? No questions right now? All right. Have a good day. I'm sorry if I fried your brain.